We're continuing on here, chapter 12, still kinetics here before we get into real 51 stuff. Now, this is real stuff. So last time we talked really about, and we did a bunch of examples on how to figure out the rate law from experimental information. Remember that the rate law is always determined experimentally. And also, as we talked about, again, is only based on reactants. So we do not have products in our rate law. And we really use that kind of experimental information to first figure out the orders for each of the reactants. Again, you could do that because you're usually given a table like we saw in those examples where you have the concentrations of each reactant, you have some initial rates, and remember that you can kind of use that formula of rate 2 over rate 1 equals Ka to the x, b to the y, and Ka to the x and b to the y. Again, as we talked about, the idea here is to really just give yourself kind of like one unknown. And so when you go to the table, as we did in those examples, we're looking for two entries where one of the concentrations of the reactants remains constant and the other one varies. And you basically put that information into sort of this formula. As I mentioned last time, it doesn't really matter, but in a lot of cases, it's sometimes helpful to take the experiment from the table that has the larger rate and put all that information up on top. It just gives you more whole numbers rather than decimal numbers, but it doesn't really matter. You can do it the other way as well. You just end up with some more decimal numbers and obviously whole numbers. You'll eventually get something like we saw, like, 4 is equal to 2 to the x or something like that. And you can solve for it. And again, if it's something that is pretty simple to look at like this, you'll know what x is equal to. If not, if you get something maybe is not as nice numbers, or maybe you did it the other way, you got more decimal type numbers, and you can take the natural log guy back to the other side, and you'll end up with obviously whatever your x value is in that case. So that's still mathematically, if you find yourself not really sure what it is, you can kind of do that. Remember that it is, because it's based on experimental information, not always going to be the prettiest of numbers, obviously. And we're going to do some kinetics experiments where your experiment numbers obviously are not going to yield you pretty nice whole numbers and stuff like that. So you may need to kind of use that along the way. Now, in the examples that we did only have pretty much two reactants. It is possible you could have multiple reactants, maybe three reactants or something of that nature as well. Probably not more than three, I would assume, in most cases. But if you kind of had a table where you had multiple reactants, like three or so, you would do the same approach. But what you would be looking for in the table is two of them staying the same concentration and one of them is varying. So the idea there is just to keep it as one variable and stuff like that. So, we have like an extra column here. We would want to find whatever entries in this table. For example, the C and the B stay constant while the A varies and stuff like that. So, and then you would kind of switch it around and stuff like that. So, um, I would say you probably most often will have two, and probably no more than three as well, is usually very common. Remember that once we get the orders for X and Y, we could add those together and get the overall order of the reaction. And more importantly, once we have the orders for each reactant, we would basically have the rate law that we would need. And again, at that point, we could then use the completed rate law to actually solve for the value of the rate constant. And remember that when you go back to this table, you can really choose any entry in the table you want to solve for K. They all should give you the same value because it is a rate constant. So it should be a constant value for that reaction under those conditions. So you could absolutely use any of the sort of entries. They all should give you the K values. You just can't mix and match and stuff like that. Any questions on any of that stuff we did sort of last time? Okay. All right. Now, we're going to talk about specific orders of reactions. And there's three very common orders of reactions. So as I just sort of mentioned a second ago, it is possible, for example, you could have a reaction maybe where there is three reactants. I would say if you think about most of the reactions you probably have seen over your chemistry career, I would say probably most of them are probably one reactant or two reactants. It's very common ones that you see. Again, not so common as maybe three. You don't see too many of that. And you usually don't see like four, five, six, seven things reacting all at once in a chemical reaction. And what that means is when we do sort of the overall order of a reaction or get the order of the reaction, there's kind of three common orders that we usually come across that we're going to talk about here. And that is first order reactions, second order reactions. We don't usually most situations come across like fourth, fifth, sixth, seventh order type reactions. Because in reality, probably to get into that sort of thing, you would need a lot of things reacting at once. You need a lot of reactants. And very commonly, one and two is probably the most common numbers of reactants that you have. And again, occasionally you could get three reactants or so. And that usually leads us to pretty much one of these three sort of orders for the reaction overall. First order, second order, or zero order is very common. So let's talk about first order reactions, which is a really important sort of order for a particular reaction, and some of the important things to sort of know by it. So there's obviously a couple ways that we could get to a first order reaction overall. We could have just one reactant where the order of that one react. It is possible as well, obviously, to perhaps have two reactants where one of the reactants is first order and the other one is zero order, right? And that would also still give you a first order overall. As we talked about, that it basically equals one. So there are a couple ways you do it. Again, very commonly here, you have just one reactant in products. We a rate expression like we talked about previously that gives us minus basically the change in the concentration of A over change of time equal K times the concentration of A. If we take the rate law here and we actually solve for K and we just look at the units associated with the rate constant for a first order units that are associated with a first order reaction, which is 1/seconds or reciprocal seconds. In reality, it doesn't necessarily have to be seconds. It's usually 1 over some unit of time. Most commonly, we do see reciprocal seconds because, like in the laboratory, we don't usually run things for weeks and days and years. We usually run it for a certain amount of seconds and stuff like that. That's usually what we sort of record the time in. And so 1/seconds is the common units associated with a first order reactions rate constant. But again, as we will see in a later chapter when we get into nuclear chemistry, 1/any unit of time is again a sort of association with that. Now, because of that, and why that is important is, as I mentioned, probably the previous time as well, there's going to be definitely a number of problems that you're going to come across where they just simply give you the rate constant and you see the units associated with the rate constant. And just based on those units, you have to be able to recognize that you're dealing with a first order reaction because they will not, with blinking lights in the problem, go, hey, this is first order, make sure you use the right ones. They're just going to give you basically the rate constant with those units and expect you to know that 1/a unit of time is basically the rate constant units for first order. Why that's important is we do have certain what are referred to as integrated rate laws for first order reactions, and this is one right here. That is the natural log of A is equal to the natural log of A naught minus KT. And these are two common graphs that are associated with a first order reaction. If we plot concentration versus time, what we will see is this graph where the concentration starts to decrease with time. Now, graph here on the left is a first order graph. We'll say that most commonly in terms of the graph associated with action, we oftentimes kind of associate the graph here on the right. And that is because when we're dealing with kinetics, it's all about straight lines basically, and we like to have graphs to show a linear relationship to what is happening. Now, when we look at this A here is like your final concentration, if you want to think about it. This is like your initial concentration. K here is the rate constant. And something that sometimes people screw up is T. T here is time, not temperature. So sometimes people at this point, it's like every time I see a T, it's temperature. So they think temperature for that, but it is time in this particular case. Now, if you take this integrated rate law and you rearrange it, so if you take this integrated rate law and you rearrange it as the natural log of A, your final concentration equals minus KT plus the natural log of A naught. This is the integrated rate law in the form of everybody's favorite equation, the straight line, y is equal to mx plus b. And that is how we get the graph that we see associated with the first order reaction on the right there. On the y-axis, there is the natural log of A. On the x is time. And when we take the slope of that line, which is m, it equals minus the rate constant. Yeah. So when we take the slope of it to figure out the rate constant, it does equal negative k. That's also important, our negatives here. That's because when I look at this line, it is a straight line, right? And that slope is a positive or negative sloping line? Negative sloping line. Slope for that is going to be a negative value, along with the second negative value that's there, will turn your rate constant into a positive value. So when you calculate the rate constant from a graph like this, if you were to do that, you should end up with a positive value for k, and that's why it is the slope is not equal to just k; it's equal to negative k, because your slope will be a negative number, and that will turn it into a positive. Any questions on that there? Now, in addition to that, as we'll see in a couple of slides, but we'll just look at it here, kind of preview it here. There is also what is known as a half-life equation for a first order reaction, and that is the natural log of 2 divided by the rate constant. If you do the natural log of 2 on your calculator, that's 0.693 divided by the rate constant. And the half-life is pretty much what the name implies. It's the time it takes for half of whatever you started with to go away. So if you started with 10, after the first half-life, you'll be left with 5. After the second half-life, you'll be left with 2.5. After that, I need a calculator, but you would keep dividing it by 2, and what will ever be left over at that point. And why first orders are really important to remember is, in addition to just kinetics problems that we're doing, as we will talk about when we get to the nuclear chemistry chapter, all radioactive decay follows first order kinetics. So all radioactive decay follows this sort of kinetics as to how they decay and decompose over the years. Now, a couple of things with this that's really important, as we'll talk about when you look at the integrated rate law, which is that natural log of A is equal to the natural log of A naught minus KT, it's really important, this part of the equation, that the time unit is in the same units. So you can't come across problems where they may give you the time in like weeks, and maybe your rate constant there is in like days or seconds or hours. So there is a time component to each of those values that are in the box. And you do need to make sure, like any other conversion, they're in the same units for everything to properly cancel out. So if you got days in one and weeks in the other, and you just use it like that, you will get the wrong answer. So you got to make sure that they're in the same units. And sometimes people sort of overlook that. The other thing that is very commonly done together is the half-life equation and the integrated rate law are oftentimes used together. So in some cases, you may not be given the actual rate constant, but you may be given the half-life for that reaction. and you would have to use the half-life equation to figure out the rate constant, and then you could kind of use the other equation with the other information to solve for whatever you're looking for. So sometimes those formulas are used together, and that's a very common way that instead of maybe giving you the rate constant, just give you something like the half-life of the reaction, and then you got to get it, use that guy to get the K, and then you can go into the integrated rate law to solve for whatever you want. The integrated rate law is basically an equation that allows us to figure out if we know, how long a reaction is running and maybe our initial concentration, how much we would expect to be there at the end, or if we know how much was at the end, we could back calculate and figure out how much we started with. So it's kind of a time concentration relationship that allows you to figure out those things, is why we kind of use these things. Questions on that? Now, in terms of what you need to know, definitely these things should be correlated in things that you do need to know. Obviously, for first order, you definitely need to be able to, again, units associated with the rate constant. You do need to know really the integrated rate law and the half-life equation. And I would say you do need to be able to recognize these as first order graphs, with probably the graph on the right there, most commonly the one that you're going to see. So those are some important things for first order that you definitely should know. All right, so let's take a looky here. So let's try one here. The reaction of 2A goes to B is first order with a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds at 80 degrees. How long will it take for the concentration to go from 0.88 to 0.14 mole? Okay, let's take a look and see how you're doing. So, a couple of things when you read this question, they were super nice to you to tell you it was first order. And trust me when I tell you, not all problems will tell you that, most will not. So, if they did not tell you it was first order, they did give you the rate constant. And once again, we see the units associated with the rate constant here is reciprocal seconds. So, again, that rate constant value that they tell you along with those units tells us it is first order, just in case they don't tell you. So again, these are things that you got to be aware of as you're going through problems so that you get it right. By the way, first order, right? Yeah. Yeah. Exactly. Yeah. So for different orders, and we're going to talk about, like I said earlier, first order, second order, and zero order, they all have different units associated with the K. If you remember, I think the other day we went through a couple that were second order overall, right? And they had like 1/molar seconds as the units. And that is like 2 letters, right, for second order. 1/seconds is like 1 letter for like first order. And again, first order and second order will have different units for the rate constant. That's how you can identify it. It does not matter in this case. It's just some extra information to screw with you. But it doesn't really matter in this particular case. Yeah. Yeah, so the only one that doesn't kind of follow that pattern is, as we'll see, zero order actually has more letters than obviously zero numbers, stuff like that. But a lot of them do. Like we saw, I think we got to a third order one, right? And then had like 3 letters. So it sort of follows that for like first, second, and beyond. Zero is a little bit different in terms of the units. We'll actually see what the units associated with it is in a second. Yeah. Other questions? All right. So since this is first order, we definitely we definitely want to roll with our first order equation, which is natural log of A naught minus KT. And in this particular case, we have our rate constant given to us. We have our initial concentration here of A, which is 0.88 molar. We have our final concentration, 0.14 molar in this case. And in this particular case, we actually do have everything that we need to solve. We're looking for time, which is T in this case. And here we don't actually need to worry about the half-life equation because we don't have the half-life given to us. And we already have the K, so we don't have to worry about kind of incorporating it. So popping this in, we're going to go natural log of our final 0.14 equals natural log of our initial 0.88 minus our rate constant 2.8 times 10 to the minus 2 reciprocal seconds and our time in this case. So what we want to do here is I personally would take the natural log of 0.14 and hit equals. I am then going to take this guy and subtract it to the other side after I do that. So going to minus the natural log of 0.88. And that's going to give me here negative 1.832838 there, before the 2. 279, that sounds good, equals negative 2.8 times 10 to the minus 2 reciprocal seconds times time. So once again, I did this on my calculator, hit equals, then took the other side and subtracted it. Now I'm going to divide this. And I also have a negative and a negative. It's just going to turn my time back into a positive, which is good. Divided by 2.8 to the minus 2. That's going to give me approximately a time that's 65.65 seconds, or approximately 66 seconds here on a little rounding situation in this particular case. Since everybody up there looks like they got like 2 sig figs, seems like a good place to lay that up at. So it will take just about a minute or so to drop the concentration of this reaction from 0.88 molar to 0.14 molar. Any questions? Yeah. Yeah, so this equation that we're using here, which is probably the one that you should remember, that is achieved by going through basically this equation, natural logging everybody to get you over there. So I would recommend probably using the natural log version of that equation is probably the better way. Yeah. They're not going to be given, so you do need to know the formulas. Yeah. Is on your calculator, is that E button there? Yeah, yeah. Yep. Other questions? So, but I say most people will usually roll with that natural log version of it, and that's probably the best one because, like I said before, a lot of the graphs and stuff that are associated with these are based on the formula for a straight line. And this version of that equation is basically the formula for a straight line. And so that's why you typically will usually see that version of it. All right, so let's talk a little bit of half-life, which we kind of obviously just did a second ago, but there is a specific half-life equation for first order, which is the natural log of 2 divided by k, the rate constant. And as I mentioned before, you may have to use both of those equations together, the integrated rate law and this one. By the way, if you by some chance you could not remember the half-life equation and you're okay in math, I suppose. You could substitute in for here the final concentration, the initial divided by 2, and solve for T, and that would give you the half-life equation if you wanted how to work it out yourself. Probably just remembering would be a much better way of doing that. So once we solve this one, what is the half-life here of N2O5 if it decomposes with a rate constant of 5.7 times? Okay, so obviously here we're going to roll with our half-life equation, natural log of 2 divided by k. In this case, it did just give us the rate constant, so we'll go right in with it, 5.7 times 10 to the minus 4 reciprocal seconds. Once again, we do want to make sure that we do use our exponent button for sure. So natural log of 2 divided by 5.7 to the minus 4. Going to get us about 1,216 seconds, or about 1,200 seconds in this case. That obviously becomes seconds when you do division of it at that point. How do I know I should use the first order one here? Is because of what? Because once again, the units here, right, of our rate constant is reciprocal seconds. So that is what tells us it is first order, and I should lay up the first order half-life equation. This half-life equation is specific for first order only, yeah. So when we get into second and zero, we'll see some different half-life formulas for it. Yeah. Just like this formula here is specific also for first order only. Yeah. Other questions? So obviously, as I mentioned earlier, the half-life is the time it takes for something to kind of lose half of what it started with. Probably about 10 half-lives, you're pretty much gone at that point. Um, and again, you can see here as we continue down, there's a certain amount of time associated with it, and it's usually the same amount of time required for each half-life to occur. All right, so why don't you try one here? The reaction of SO2 Cl2 makes SO2 and Cl2's first order rate constant 2.9 times 10 to the minus 4 reciprocal seconds. Find the concentration of SO2 Cl2 at 865 seconds when you started with 0.0225 molar. So take a few moments there, see what you come up with. Okay, let's take a look and see. So once again, they were nice enough, but they won't be. So once again, we do see the units associated with the rate constant are reciprocal seconds. So again, that is the key to know, hey, I should start using my first order sort of information, right? So you want to always kind of keep that in mind because obviously at this point we only have a couple to choose from, but we will have more formulas to choose for shortly. And you want to make sure that you are using the correct ones. And again, it is based off of the units that we see associated here with our rate constant. So again, we're going to use our natural log of A is equal to our natural log of A naught minus KT. We obviously have the K given to us. We are looking for really our initial concentration, no, our final concentration actually, is what we're looking for. Our initial concentration is 0.0225 molar, and our time in this case is 865 seconds. So we do have really everything we need. We got everything on the right-hand side here, and we can basically just plug it in. Now we got our natural log of A is equal to our natural log of 0.0225 minus our K 2.90 times 10 to the minus 4 reciprocal seconds, and our time here 865 seconds. So this is what I was referencing earlier. You do want to always just make sure the unit of time in both of those are the same units. They're both seconds in this case, so we're going to be good. But there definitely will be times where they will be different time units, and you got to do that conversion. So just also keep that in mind as you go through it. So we're just going to kind of clean up everything on the right-hand side. Just going to put in my calculator exactly how it's written. So natural log of 0.0225. I'm going to hit equals. I'm going to hit minus, going to open me parentheses and go 2.9 exponent button -4 times 865. All said and done there, we end up with the natural log of A is equal to minus 4.04508997 on my calculator. To get rid of the natural log on that side, we need to take the E of both sides on your calculator there. And basically you're just gonna pop both of these guys into the E. When you do that, that pretty much gets rid of the natural log on that side. And on most people's calculators, I would say that button is found kind of like above the natural log button on most people's calculators. Mine happens to have a individual button, but on most it's kind of above that is what you're looking for. And if you do that, you're going to end up here with a 0.0175 molar in this particular case. Yeah. As our final concentration. Question. Now, a couple of things that hopefully should make sense is it is decreasing with time. So if you ended up with a higher concentration than you started with, you're definitely going in the wrong direction. Yeah, so something did not go right there. Also, it actually, for this particular reaction, based on the rate constant, you're looking at about 2,300 seconds or so for it to go through a half-life. So at 865 seconds, it is less than one half-life. So our answer should be higher than half of that first initial value as well, which it is. So we're all good in this particular case. So those are some things. If you're really curious what the half-life is, you could put the rate constant into the half-life equation, and it'll tell you how long it takes, and they can judge where your answer is. That question or answer. All right. All right. So molecular iodine has a rate constant of 0.271 reciprocal seconds. What is the half-life of this one? Okay, so once again here, we know it's definitely first order, rate constant there, units. Going to go right in there to our formula, natural log of 2 divided by 0.21 reciprocal seconds. That is going to get us here, looks like about 2.56 seconds is the half-life in this particular case. That would say is super, super fast. Yeah. So like every 2 seconds, half of it goes away, or 2.5 seconds, every half of it goes away. All right. The next order of reaction we're going to talk about are second order reactions. So again, what we just were talking about is specifically related to first order reactions, and those are the equations that's used for that. Let's talk about what we got going on with a second order reaction and sort of the important parts of it. So just pop it all up there. So once again, you can get a second order reaction a couple of ways. You could obviously have one reactant where it has a order of 2, right, which would give you a second order overall. You could also have 2 reactants where each one is first order. That will also give you obviously second order overall. You could also have 2 reactants where one is second order, one's zero order, and that would again give you a second order overall. So overall, there's a few different ways you can kind of get there. Looking at our sort of rate law for a second order, if we again rearrange it and solve for K over here, the rate constant, we do see some different units here developing for the rate constant for a second order reaction. So 1/molar seconds are the typical units associated with a second order reaction. Just like first order and really any kinetics, the unit of time here does not necessarily have to be seconds. You could have something like 1/molar minutes or 1/molar hours. That would still be second order. It's really 1/molar times some unit of time. Once again, the most common unit of time that we deal with is seconds. So you do see seconds a lot associated with it. And just like the other one, you could write this as m to the -1 or s to the -1 as well. And that's again just another way to display it. Now, we do have an integrated rate law or concentration and time dependent rate law or formula for it, which is this one here. And that is 1 over the A, concentration of A. That's the same deal. That's like our final. This is still our initial, 1 over the initial. That is still our rate constant. And that is still time in this case. Now, also different is the half-life equation associated for a second order. It's a little bit different than the half-life equation that we do see for our first order. It's 1 over K times the initial concentration. So unlike first order reactions where the half-life is independent of the initial concentration of the reactant, here for second order, the initial concentration does play a role in the value of the half-life based on what it is. And obviously here, the larger we have of our initial concentration, it's going to again have an effect on our half-life. You may actually see a larger half-life happening in that particular case. So we do have a typical graph, and just like the first order one, we could take this equation, 1 over the final concentration equals KT plus 1 over the initial concentration, and this would rearrange that into the form of a straight line of y is equal to mx plus b. And this is again how we get the graph that's associated with this. On the y, we're going to graph 1 over the concentration of A. On the x, we're still going to do time. And that will once again yield us a straight line. The difference, though, with our second order is our line is actually having a positive sloping line. Yeah. So we do have a positive sloping line happening here. That also affects the slope of that line. The slope of this line actually just equals K because the slope of that line is going to be positive, and a positive number will give you a positive number for K in this particular case. So kind of the same pieces of information and the same deal. You may sometimes have to use both of those formulas together if you're just given the half-life. But the important things for your second order is kind of similar. You want to make sure you know the units associated with a second order reaction. You definitely want to know our concentration time equation, our half-life equation, and obviously, once again, the graph that's associated with a second order graph. So if you lay up this graph and it's linear, you probably are dealing with a second order reaction. If you put the graph we saw previously, the natural log of A versus time, and you get a linear line, you're dealing with a first order. So graphs are all over the place in kinetics in terms of you see them in a lot of places, and that's how a lot of information is represented to you. So much like having to know that the units associated with K is for a specific order reaction, you also have to kind of know the graph when you look at it. Oh, this is a pretty linear graph. This is what is graph. That tells me first order, or that tells me second order. So the graph aspect of it is also really important in kinetics because you do come across a lot of them. Any questions on that? Yeah. Say again? Uh, it's just the way that this reaction proceeds is the concentration is not necessarily increasing over time. 1 over the concentration is increasing over time, right? In this particular case. Yeah. So if you have 1 over, I'll get something right with there. So yeah, camera erase. So let's just say we had, the concentration was 5, and that's the reaction is going, it's getting smaller, 3, 2, and so forth, right? So what we're actually seeing here, right, is not the actual concentration, and we're seeing 1 over it. So if we take 1 over 5, right, we go 1 divided by 5, got 0.2, 1 divided by 4, 0.25. So you can see the pattern there when you do 1 over the concentration. It is technically decreasing with time, right? But the relationship that we see here when we do like 1 divided by 3, we're now at 0.33. So by graphing that, we're not graphing just the concentration. What we actually seeing increasing is it actually is decreasing with time, right? And that's going to, when we do the 1 over the concentration, that's why we see the graph is sort of increasing, if that's your question of what's happening in that case. Yeah. Yeah. It is for second order. It's the only one that you'll come across that has a positively sloping line. And again, that's a really quick way to recognize it. First order is always going to have a negatively sloping line. And as we'll see here in just a second, zero order will also have a negatively sloping line. So the second order sort of graph will always be the only one that's sort of positively sloping. And again, that sort of 1 over relationship also affects the half-life as well, because again, as you can see, as the concentration sort of goes down, with that how will have the similar effect on the half-life in terms of it going up or down depending on concentration. So looking at the next sort of order reaction, the last one that you'll really be responsible for and most commonly found are zero order reactions. And zero order reactions are also a little bit different in terms of the formulas that we use associated with it. Um, once again, here you could get a zero order reaction by obviously having somebody to the zero order. And that would give us a rate law of the K is equal to A to the 0, which means the rate law equals K. And if you put that in there into here, since that's going to cancel out, the units associated with a zero order reaction are actually the same units that you associate with just the rate of something, molarity over seconds. So again, on the three sort of orders of reactions that we've talked about and that you are responsible for, again, they all have different units associated with that K value. Again, the first order is reciprocal seconds or 1/time. The second order is 1/molar seconds. And now here our zero order is molarity over seconds. So again, these are things that you don't want to kind of overlook because it can help you obviously solve a problem by identifying what you're dealing with. Again, if you have something with just molarity over seconds as the rate constant units, you know you're dealing with a zero order reaction. In this particular case, the kind of concentration time formula for a zero order reaction is very similar to first order, except there is no natural log happening there. So it's basically similar to it. It's the concentration. The final concentration is equal to the initial concentration minus K, our rate constant, times time. The half-life here also is dependent on the initial concentration, and it's the initial concentration divided by 2K is the half-life equation associated with it. Just like all the other ones, if we rearrange that sort of formula there for time and concentration minus KT plus R A naught, once again, that is going to give us our formula for a straight line for this one. And that's going to get us here, our Y is equal to MX plus B. So the typical graph that is associated with a zero order is the concentration on Y, the time on X. That is again going to get you a linear relationship in line with a negatively sloping line like we just talked about. So the line is similar to what you see with first order. They are both negatively sloping line. As the earlier question was, second order is the only one that kind of goes in the other direction. So that's a really easy way to recognize it as well if you're doing some type of graphing. The slope here, once again, is going to equal negative of the rate constant. That again is because you have a negatively sloping line, and that negative is going to turn it into a positive number, which is going to give you, again, a positive value for the rate constant, which you want here. Now, you may remember that when we looked at first order, we also saw this exact same graph, which was the concentration versus time. But it did not look the same when it was first order. It was not a linear relationship. It was more of a decreasing with time sort of relationship. So these are two of the same graphs, same things being graphed. But if it's a first order, it will not give you a linear relationship if you graph concentration versus time. But if you do get a linear relationship of concentration versus time, it definitely is going to be a zero order. So these are two things that are same things graphed, but the graphs do not end up the same. So one's linear relationship and one is not a linear relationship. So just like previously in terms of things that you should know for a zero order, once again, your units, your equations here, and then also, once again, the graph associated with it. Any questions on that there? Correct. So this is first order. This is technically a first order graph. I didn't draw super great there, but it's decreasing with time sort of graph. But the one that most people associate with a first order is the linear graph, which is a natural log of A versus time, which gives you that linear relationship. If I could draw a straight line there. Yeah, yeah, yeah. The natural log is really the graph that most people associate with a first order reaction. But this is also associated with the first order reaction, sort of the nonlinear relationship. But sometimes people get confused because they will sometimes show this graph, and then you come to this graph and you got that linear relationship, and sometimes they get them confused. So it has to be a linear relationship if you're graphing these two things for it to be a zero order. If it's not a linear relationship, when you're graphing those two things, it's more like what we saw earlier and kind of badly drawn there. It's going to be more of a zero order that you're doing. Correct, correct. Yeah. So Yeah, so before you basically take that formula with the natural log, that's what it would sort of graph like, and then you end up with the guy on the left there once you do. Other questions? So again, first order, zero order, and second order, you need to know all those things that we just highlighted. So let's take a look at this one. We have this reaction that is second order in Q. If the initial concentration of Q is 0.01 molar and after 5.0 times 10 to the 2 seconds, the concentration is 0.001, what is the rate constant in this particular case? See something. Okay. Okay, let's take a look. So here, obviously, they tell us a second order, so we should think about our second order sort of equations here. And that's going to be 1 over A is equal to 1 over A naught. And this is plus KT, not minus. And in this particular case, we do have our initial concentration there of 0.01 molar. We have our final concentration 0.001. We do have our time, which is about 500 seconds, right? So we got everything we need here to figure out K. So we're going to go 1 over our 0.001 equals 1 over 0.01 plus our K and our time here, which is 500 seconds. Once again, I'm going to do 1 over 0.001, and then I'm going to take this guy and subtract it to the other side. So I'm going to go 1 divided by 0.001. I'm going to subtract it. You can see about 1,000. 1 divided by 0.01. And that's going to get me about 900 over here. By the way, the molarity is on the bottom here. And that means basically got 1 over molarity there. Gonna go equal to K times my 500 seconds, which then gets divided to the other side. And when I do that, they're gonna get me a 1.8 1 over molar seconds as I take the seconds and divide it to the bottom with the molarity that was there at that point. Question on that? So if you are not getting the right answer, you might want to think about punching in your calculator in steps. Yeah, not punch everything in together. Don't be afraid to use the equal sign. So once again, mathematically, I would do 1 over that and hit equals. I then would hit the minus and do 1 over this and hit equals. And then I would hit the divide that. And you should hopefully get to the right answer. So don't be afraid to hit equals along the way there. So you do end up with the right answers. Any questions on that there? All right, so let's try this one here. How many minutes would it take for the concentration of A to go from 1.25 molar to 0.433 molar in this zero order reaction? The half-life of A is 22 hours. Let's see what you come up with. Take a look. So obviously here is zero order, so we should pull out our zero order formulas. That is like A is equal to A naught minus a K. Okay, T. A little half-life equation of little natural log divided by 2K, I think. I know it's reassuring when I say that. All right. So here in this case, we are looking for how many minutes. So we're really looking for time it will take for the concentration to go from 1.25, which would be our initial concentration, to our final concentration there of 0.433 molar. We do have the half-life given to us of 22 hours in this case. So if we take a look at our sort of integrated rate law here, we are looking for time here. We do have that. We do have that. We are once again here kind of missing the rate constant. But we are given the half-life here, so we can use our half-life equation to get to the rate constant so that we can solve for it. Now, it is really your call, but I personally, at this point, since I know I do want my time to be in minutes, I'm just going to kind of convert the hours to minutes up front, so everything will be in the right unit. You don't necessarily have even in hours to kind of do the conversion at the end. So you might get slight numbers if you didn't convert it up front. But in the end, it should ideally come to the same thing. So we got an hour is like what they say there 60 minutes, I think. Hopefully. Never know, things change. Here we go. It's like 1,320 minutes. All right. So I got that. I'm gonna go 1,320 minutes equals my initial concentration 1.25. 1.25 times 2 times K. Basically, these two guys will swap part places, basically, and K will equal 1.25 divided by 2 times 1,320. And here, 1.25 divided by 2 times 1,320. That's going to give us a rate constant of 0.000473. And the units here, molarity up on top, that is minutes actually on the bottom. So that would be molarity over minutes would be my units associated with it, which again is the typical units we associate with a first order, right? Molarity over some unit of time. Now that I have all I might need here, so we're going to go in with our final concentration 0.433, no more threes, and 1.25 minus our K we just calculated there, 473 molar minutes, and times our time. So we're going to go 0.433 minus 1.25, hit equals. That's going to get us something like negative 0.817 is equal to negative 0.000473 molar minutes in our time. Going to do a little dividing action there, right? And 0.000473 are going to yield us, I'll go with maybe like 1,727 minutes with some bad rounding there along the way. Any questions on that? So again, like I said before, very commonly with sort of kinetics, half-life equation, kind of integrated equation, sometimes has to use it as they sometimes will give you half-life. I would say definitely when we get into the nuclear chemistry chapter, that's a very common sort of problem you'll come across. It will deal with first order kinetics, but very commonly they just kind of give you the half-life. You kind of have to use that for the other. Is it 170? I got 1727 on mine. Anybody else get that? Yeah. Yeah, so what's that? Are you asking should it be 1727.2 or point or 172.7? Let me just double check, make sure I didn't lose decimal there. So we're good with 0.000473 as the okay, so 0.433, right? Minus 1.25. That gives us 0.817 divided by 0.000473. I got 1727. There's 3 zeros. Did I have too many zeros there? I did. Yeah, for sig figs, really,